everyone, welcome to another video. Here is a question on trigonometry, that's advanced trigonometry, and the question reads: a vertical tower of height a feet high is surrounded by a flagstaff from a point on the same horizontal level as the base of the tower. Okay, now we are given that the angle of elevation of the top of the tower is alpha, and the angle of elevation of the top of the flagstaff is alpha plus beta. So we are asked to prove that the length of the flagstaff, that is the length of the flagstaff, is equals to this identity. Okay, now the first thing we need to do, which is our first inclination, is to draw the diagram, to analyze this problem. We need to draw the diagram and let's see what it looks like. Okay, now, and to do that, we're going to go back to the question again. We have a vertical tower of height a feet. So let's say we have, this is a tower. Okay, the height of the tower, okay, this is the tower. A is the, let me label the top of the tower to be A, letter with a letter A. So the height of the tower to the ground is A feet, okay, then is surrounded by a flagstaff. So let's say we have a flagstaff. This is a flagstaff. So this is A. Now this is the top of the flagstaff. Okay. Now the length of the flagstaff, let's take the length of the flagstaff to be L. The length of the flagstaff is L. Okay, so we have that from a point on the same horizontal level as the base of the tower, the angle of elevation of the top of the tower is alpha. So this is the top of the tower. Okay. Okay, this is the top of the tower. So the angle of elevation from a point on the same horizontal level as the base of the tower. So if we label the base of the tower to be B, okay, so that means the angle of elevation, okay, of the top of the tower. This is the tower. Okay, this is the tower. This is the tower. Okay, now this is the flagstaff. We have this flagstaff in this case. So from the top of the flagstaff, okay, because we have angle of elevation here to be alpha, then also the angle of elevation of the top of the flagstaff is alpha plus beta. So that means I'm going to draw a line, okay, from to the same point on the same horizontal level, Now let's say the horizon, now this point is labeled with letter C. Okay, so the angle here will be beta and this is alpha. So which means the angle of elevation of the flagstaff will be the sum of alpha and beta. Okay, so now the base, which is the horizontal, will be, let's label the horizontal with letter L. So I can say let L equals to length of flagstaff. Okay, then we know that, then we can also represent horizontal distance. Okay, horizontal distance BC is D. Okay, all right, so now we want to prove this identity. Now to prove the identity, I'm going to start with triangle ABC, and you can see the triangle is a right triangle. So for triangle ABC, so I'm going to write in triangle, that is a right angle triangle ABC, So we know that by using what we call the SOHCAHTOA, SOHCAHTOA is a suffix used in trigonometry, for finding or determining the unknown side, or the unknown side and angle in a right triangle or in the triangle. Okay, so in this case, we have the opposite and this is the adjacent. So we are using tan alpha equals to opposite over adjacent. Okay, so the opposite is the what? The height of the tower. The adjacent is the what? The horizontal distance, because opposite, that is the the side which is directly opposite the given angle, which is alpha. So in this case, we're going to have tan alpha to be equals to, opposite is A, adjacent is D. Now let me express D in terms of what? In terms of A. So in this case, we're going to have D to be equals to A divided by tan alpha. So let's call this equation 1. Okay, let's call this equation 1. So this is equation 1. Okay, all right. Now, I will then again look at triangle TBC, right angle triangle TBC, because now I need to consider the Flagstaff, okay, and its angle of elevation. So TBC, so in triangle TBC, T is the top of the Flagstaff. In triangle TBC, so we can see that we're also going to use tangent, that is SOHCAHTOA. So in this case, we know that the height in this case will be the length of the Flagstaff plus the height of the tower. So that means we're going to again use tangent of, now let's not forget that angle of elevation of the Flagstaff will be sum of alpha and beta. So we have alpha plus beta equals to opposite over adjacent. Okay, so that this will be tangent of the sum of alpha and beta. The opposite, like I said, will be the addition of length of the Flagstaff and the what? The height of the Flagstaff. So that will be A plus L. Then the adjacent is what? D. The adjacent is D, which is the horizontal distance. So again, I'm going to express D in terms of A plus L. So that means D in this case will be A plus L over tan alpha plus beta. Now, this is the second equation. That's the second equation for D. Now, we can now equate equation 1 and equation 2. Now, equating 1 and 2. For 1, we know that that is A divided by tan alpha equals to A plus L divided by tan alpha plus beta. Let's not forget that our goal here is to make L the subject of the formula. So what we do in this case is to cross multiply. So when we cross multiply, this will be A, product of A tan what? Alpha plus beta equals to the product of A plus L and what? Tan alpha. That's it. All right. Now, in this case, on the right hand side, I'm going to distribute tan alpha so that this will be A tan alpha plus beta equals to A tan alpha plus L tan alpha. Remember, our goal is to make L the subject of the formula. All right, so I'm going to move this guy to the left hand side so that on the left hand side we can have A tan alpha plus beta minus A tan alpha equals to L tan alpha. So in this case, I'll divide both sides by tan alpha so that I can isolate L. Okay, divide both sides by tan alpha so that we can have tan alpha. Let me rearrange it to be tan alpha to be equals to A product of A tan alpha plus beta minus A tan alpha, okay, divided by tan alpha. Okay, sorry, this will be L. Okay, this is L. That's it. All right. So now let me factor out A. And then let's not forget that the definition for tangent, like if you have tan theta, for example, that will be sine theta over cos theta. So I'm going to write this in terms of sine and cosine. All right. So that means this will be L equals to A open bracket. So this will be sine alpha plus beta over cos alpha plus beta minus this will be sine alpha over cos alpha. Okay, Then we divide it by, so this will be divided by, it will be divided by tan alpha, which is same thing as sine alpha over cos alpha. Now, this is the division bar, okay, slash. I use that to represent the division bar. So this is the numerator and that's the denominator. All right, so let's simplify this, okay, let's simplify the numerator. So we can say from here that L equals to A open brackets. So in this case, I'm going to perform what we call algebraic multiplication. So it's cos alpha multiplied by sine alpha plus beta. So I'm going to have that to be cos alpha, okay, multiplied by sine alpha plus beta. Then sine alpha multiplied by cos alpha plus beta. So this is minus sine alpha, then cos alpha plus beta, okay, all over. So I can also I'm going to multiply these two. So this will be cos alpha, okay, cos alpha plus beta, all over this. That is sine alpha over cos alpha. That's it. That makes sense. All right, so now, when we look at the numerator, now I can bring this here because, it's just like when we divide two fractions, okay? This is a fraction. So I'm going to, when we divide this by this, then I'm going to flip the fraction under so that L will be A. In this case, this is going to be cos alpha sine alpha plus beta minus sine alpha cos alpha plus beta. Oh, let me manage the space. Okay, so we have L to be equals to A open bracket cos alpha sine alpha plus beta minus sine alpha cos alpha plus beta divided by cos alpha, then cos sum of alpha beta multiplied by cos alpha over sine alpha, because this is going to what? I'm going to flip that. All right, so if you look at cos alpha sine alpha plus beta minus sine alpha cos alpha plus beta, this is same thing as when we consider the sum to product identity for sine. That is, when we look at, okay, applying the sum to product identity for sine, let's say sine A plus B, we know that this will be sine of angle A cos B plus, so this is, in this case, it will be minus, okay, so this will be cos A sine B. So let's treat alpha plus beta as A and then alpha as B. So that means we can write the numerator, this guy here, and let's not forget that cos alpha will cancel cos alpha. So we'll be left with sine alpha cos alpha plus beta. So this will be A open bracket, this will be sine of alpha plus beta, okay, sine of alpha plus beta minus alpha, okay, minus alpha, close parenthesis. So all over, remember we want to prove this identity, so all over sine alpha times cos alpha plus beta, that will be sine alpha then cos alpha plus beta. Okay, so that L will be equals to A. So if I remove the parentheses in this case, so this will be A open bracket sine alpha plus beta minus alpha, okay, divided by sine alpha cos alpha plus beta. So alpha minus alpha, that will be 0. So we have L to be equals to A sine beta divided by sine alpha cos alpha plus beta. And we just prove that the length of the Flagstaff is equals to the product of the height of the tower and the sine of beta divided by the product of sine alpha and the cosine of the sum of alpha and beta. And we've come to the end of this session. The noblest pleasure is the joy of understanding. Bye-bye.